Hello everyone, welcome to this sixth lecture in the NPTEL course on Riemannian geometry. So today we'll continue with our review of smooth manifolds, and this will be the final lecture in the review of smooth manifolds before we move on to the main topic of the course. So if you recall, last time we talked about tangent spaces and vector fields. So let me just quickly remind you that a tangent space at a given point, there are various equivalent ways of defining it. One is you can think of it as the set of all possible directional derivatives at P, or in fancier language the set of all derivations at P. A more geometric way of thinking of them is essentially the set of all velocity vectors of curves. So we formalize this by defining an equivalence relation on class of curves passing through this point P, and so then you can define the tangent space as the equivalence class of curves passing through P. And it turns out that the tangent space is an n-dimensional vector space if x1 up to xn are local coordinates. Then one can define these derivations del by del x1 up to del by del xn. So these are the analogues of the usual partial derivatives from calculus, and it turns out that they in fact span, they are linearly independent and they span the entire tangent space. So next we had introduced vector fields. So this fancy x of M is the space of all possible vector fields on M. So locally on an open set with coordinates x1 to xn, I can write any vector field x restricted to U as a linear combination of these basis tangent vectors. So the components need to be then smooth functions on this open set. So that is, if you remember, the definition of vector fields had two components. Firstly, the value of a vector field at a point P must belong to the tangent space at that point, and secondly the vector field must be smooth. Smooth basically means exactly this statement. So then given any smooth map between two manifolds, one can define the derivative of that map as a linear, so this is a linear map between the tangent spaces. Okay, and then the derivative has this very beautiful property that the derivative of compositions is the composition of derivatives. So that's basically the chain rule from calculus. Okay. So today I am going to talk about the cotangent space, the dual of the tangent space. So the first thing I want to talk about is the cotangent space. And after that I'll define general tensor fields. Okay, so here's the definition. So define the cotangent space at a point to simply be the set of all linear functionals on the tangent space. So alpha is a linear map from the tangent space into R. Okay, so from linear algebra we know that if a vector space is n-dimensional, its dual is also n-dimensional. So the dimension of this thing is also n, and in fact one can again write down a basis. So if x1 up to xn are coordinates, near P, then one can write down a basis for the cotangent space. So this is the span over R of these quantities, where this dx1 up to dxn is basically just a dual basis to the del by del x1 up to del by del xi. So that means that if you apply dxi at P to del by del xj at P, then that's going to be the Kronecker delta symbol, delta ij, which basically means that, I mean, this delta ij is 1 if I is equal to j, and 0 if I is not equal to j. Okay. So this is the dual basis to the basis del 1 up to del n. Okay. So again, when you have a basis, you also need to know what is the change of basis or transformation formula. So we have the following change of basis formula. So if y1 up to yn is another set of coordinates, and if you write del dx at P to be basically the row vector consisting of the basis with respect to the x coordinate system. So this is the row vector given by dx1 up to dxn, and similarly dy is the row vector in the y coordinate system. Then we have the following transformation formula, that dy is simply the row vector dx multiplied by del y by del x. Okay, just for comparison, for the tangent space, we had the following transformation formula. Okay, so the transformation formula for the dual basically has the inverse of the Jacobian matrix that shows up in the transformation formula for the tangent space, right? So note that these are inverses of each other. Okay. All right. So one can then, similar to the tangent space, one can then construct the cotangent bundle so T star M, this is just the disjoint union of the cotangent spaces at each point, and again this is a smooth 2n dimensional manifold and if you look at the natural projection map, this can be given the structure of a vector bundle. Okay, so similar to how we had a notion of vector fields, so these were maps from M to the tangent space. Similarly, one can define maps from M to the cotangent space. So these are called one forms. Or a co-vector field. Is a map alpha from M to the cotangent space such that again the composition with the projection map is the identity, which basically means that alpha at P, which we will sometimes denote by alpha P, is a covector in the cotangent space at P, and second, alpha is again smooth in the following sense: for any choice of coordinates on the open set U, you can write the restriction of alpha to U as summation I going from 1 to n alpha I at P times dxi at P, and these alpha i's have to be smooth functions. So let me also say a word about the notation used. The components of a vector field let's say xi of a vector field X are denoted with an upper superscript. Okay, so you denote it like this, right? Whereas components of a covector field are written as subscripts. So we write alpha as summation alpha I dxi. So here this is a subscript. Okay. So that is just a convention that's followed universally, and so we'll also do the same. Okay. So essentially the simplest sort of non-trivial example of a covector field is given by the following. So suppose you have a smooth function on n, right? Then one can look at its derivative map. So the derivative map is the derivative at any point is basically a map between the tangent spaces, but the tangent space to R at any point can be identified with R, right? So that means, and the derivative is a linear map, so DFP actually gives you an element of the cotangent space at P, okay? So this means that if you take DF as you let P vary, this will actually give you a one form, and in fact locally DFP is precisely the summation I going from 1 to n del f by del xi at P times dxi at P. Okay. So this is a standard example of a one form. So the set of one forms or covector fields is denoted by A1 of M. Soon towards the end of today's lecture I am going to define the set of K forms, where K could be any number between 1 and n. Okay, so this 1 basically stands for forms of degree 1. So the set of all 1 forms is denoted by A1 of M, and this is again a C infinity of M module. Okay. So last time for vector fields I explained what that means. You can essentially transport the same definition for even 1 forms. Okay. So Alright, an important remark is that a one form alpha actually gives a C infinity of M linear map from the set of all vector fields to the set of all smooth functions. So a vector field gives you alpha applied to x, that's a smooth function. What is alpha applied to x? Well, for all p in M, the value of this function at p is precisely alpha p applied to xp. Remember, alpha p is a covector in the cotangent space, so that means it gives you a linear function in the space of vectors. Xp is a vector, so alpha p evaluated at xp is a real number. Okay, so for each p, alpha of x gives you a real number, and in fact as p varies, this alpha x of p also varies smoothly. So alpha of x gives you a smooth map on a smooth function on M. Okay, so now I can define what are sort of general tensors on M. So here's a definition. A tensor T of type AB is a C infinity of M multilinear map it's a C infinity of M multilinear map on a bunch of one forms comma a bunch of vector fields. So basically you take a number of one forms, so that is this A, and you take b number of vector fields, then T will basically spit out, so as an input it will take a number of one forms, b number of vector fields, and it will spit out a smooth function, right? And it's supposed to be multilinear in each of these entries. All right. So then we denote by T upper A lower b to be the set of all tensors of type AB. So there are some special cases. So for instance, if you take A equal to 0, B equal to 1, right? So then a tensor is just a C infinity linear map from the set of vector fields to this space of smooth functions, but we saw that that's basically just a one form, right? So one form gives you a C infinity linear map from this. So T01 is basically just the space of one forms. And then you can take sort of the dual version of this. So if you take A is 1 and B is 0, so this is the set of linear maps from this, then that's essentially just a vector field, right? So given a vector field X, you define a map Tx where alpha, a one form, goes to alpha of x, okay. So that means that the space of tensors of type 1, 0 is basically the same as the space of vector fields, okay. So these tensors actually generalize both vector fields and one forms. All right. So locally, one can write this tensor as the summation over I1 up to IA, J1 up to JB. So these are all elements in the set 1 to n. So these are indices in this set 1 to n, and a tensor generally has this form. So maybe let me write a bit bigger. So these are points in the set 1 to up to n. So it will have upper indices I1 to IA, lower indices J1 to JB, and then tensored with dx J1, tensored etc. up to dx JB. Okay. So these quantities Ti1 up to Ia, J1 up to JB are called components of the tensor. Okay, so just as an example, if you take A is 0 and B is 2, so this is going to be the most relevant tensor for us. Next lecture we are going to introduce Riemannian metrics. They will basically be 0 2 tensors. So that can be written in coordinates, for instance, as Gij dxi tensored with dxj. Okay. Similarly, you can take for instance when we define curvature, that's going to be a 1-3 tensor. So you can take A is 1 and B is 3. Then the curvature tensor is going to be of the following form: IJKL R I JKL del I tensored with dxj tensored with dxk tensored with dxl. So this is the way we write tensors in local coordinates. Okay. Alright, so the key proposition regarding tensors is the following. So this is essentially the fundamental property of tensors. So let alpha 1 up to alpha, with upper, let's say. So let alpha 1 up to alpha A be some 1 forms, and let x1 up to xb be some vector fields. Suppose you take a tensor of type AB and let's say P is some point in M. So suppose alpha I at P is 0 or xj of P is 0 for some, you don't even need it to be for all I and j, just for some I or j. Okay. So suppose one of these covectors or one of these vector fields is 0 at this point P, then the conclusion is that if you apply the tensor to this. This is now going to be a function on M by the definition of what a tensor field is. So if you evaluate that function at P, that's going to be 0. Okay, so as long as one of these covectors or vectors vanishes at this point P, it doesn't matter what these vectors, covectors do elsewhere, the value of this tensor is going to be 0. Okay. Right. So a consequence of this is that for all P and for all tensor fields, this tensor field T actually induces a R multilinear map which we denote by TP from A copies of the cotangent space times B copies of the tangent space to R. Okay. So how do you define this this map? So given given these covectors, a number of covectors, so here as usual this is A and this is B. Okay, so given A covectors and given B vectors, let alpha 1 alpha A be any form and x1 up to xb be any vector fields such that alpha I evaluated at P is this covector omega I, and similarly xj evaluated at P is this vector Vj, right. So that means you take these covectors and vectors and take arbitrary extensions to one forms and vector fields, and you just simply define Tp of omega 1 up to omega A, sorry, maybe I'll just write it in the next page. So you just define as simply the tensor field applied to these forms and vector fields. That will give you a function, evaluate that function at P. So the fundamental property of the tensors tells you that this definition is independent of the extension you pick. So the way you extend these covectors and vectors to one forms and vector fields, that doesn't matter by our fundamental property of tensors. So the key upshot is that given any tensor field, you actually get a pointwise multilinear form on your on a collection of A cotangent spaces and B tangent spaces. Okay. All right. So to end today's sort of final lecture on the review of smooth manifolds, I will conclude by talking about differential forms. So a K form is simply a 0K tensor which is skew symmetric. Okay, so that is if x1 to xk are some vector fields, then alpha x1 up to, you take any I and switch these two together, then your form will change by a sign. So this is minus alpha times x1 up to xi plus 1 xi up to xk. Okay, or more generally, if you take a permutation sigma over k elements, then alpha of x of sigma 1 up to x of sigma k, that's going to be the sign of the permutation times alpha of 1 up to alpha of k. Okay, and then you call ak of m to be the set of k forms. Okay, and locally we write them as follows. So let's say x1 to xn are coordinates on some open set U, and let's say alpha is a k form, then alpha on U is written as the sum over all these indices j1 less than j2 less than jk of alpha j1. Again, because it's a k form, you write with a subscript, and because it's a tensor of the form 0k, right? dx j1, and then instead of tensors, to remember that these are skew symmetric, you use the wedge product. And the reason why none of these indices, a ji is not equal to a jl, is because if two of these indices are the same, then by skew symmetry you would anyway get 0, right? So in the local expression we need these strict inequalities. Sometimes it's actually convenient to forget about the ordering, so then you take 1 by k factorial over all possible indices, and then remember that by skew symmetry, if two of the indices are equal, then anyway you get 0, right? So those things do not contribute to this sum. Okay, let me end with just stating some basic properties of forms. So basic operations on forms. So one, we have the wedge product. So this takes in a k form and an L form and spits out a k plus L form. Okay. So I'm not going to write down what this means. You all already know this from your smooth manifolds course. So let me just remind you that the set of k forms is trivial if k is larger than n, right? So it's strictly greater than n. So it actually makes sense to talk about K forms only when K is between 1 to n, and our notation usually, sometimes it's also convenient to talk about 0 forms. So a 0 form is simply a smooth function. Okay. All right. Then we also have this thing called as the interior product. So here you take a K form, you take in a vector field and you get a K minus 1 form. So Ix of alpha applied to K minus 1 entries is simply alpha x comma x1 up to xk minus 1. Okay. Then third, you have the pullback operation, that if f is smooth, you have the pullback map which takes in K forms on n and gives you K forms on m. So f star alpha will now be a K form on m. So it takes in K vector fields and spits out this number. So you push forward the K vector fields by the derivative map and evaluate alpha on that. And finally, we have the exterior derivative. So this pushes the degree up by 1. Okay. So this is the unique, R linear map with the following 3 properties. So on functions, on 0 forms it does this. Then if you take the wedge product of 2 forms, you have some sort of a Leibniz rule. So this is a Leibniz rule. Minus 1 to the degree of omega, omega wedge d eta, and finally you have that d squared is 0. So it turns out that all these 3 properties are enough to define a unique operator which is R linear. So it takes a form of degree k and gives you a form of degree k plus 1. Okay, so yeah, maybe I'll stop here. So so this essentially finishes our review, a very sort of quick review of smooth manifolds. Next time I'll actually introduce Riemannian metrics, and we'll really, I mean, from the next lecture we'll really start this course in the true spirit, right? So in the truest sense, we'll start this course from next lecture. All right, so that's it for this lecture, and thanks for your attention, and I'll see you in lecture 7.